So this is a function fx. Okay. So if you draw one vertical line or horizontal line, so if you see it's a horizontal line, if you draw, it has to cut the function at most once. Okay. So here you see the function. If you draw line, this type of line, so this line won't touch the function. But if you draw a line like this, it will at least touch once. It will touch exactly once. So this function is not one to one, but this is on to, because each line is parallel to y-axis. If you draw, then it will cut. But if it is not, if you are drawing the lines through x-axis, like parallel to x-axis, then it won't touch y. So when the function which is in a real number, from set of real number to set of real number, then you can use these two tests. You can note down. Also, I will be sharing this PDF with you guys. So these two tests are like you can use for the function to be one to or on to in when the function is from set of real number to set of real numbers. So now the question is, if it's the function is changed, the function is, if you change the function, it means if you change the domain and codomain. So function is from natural number to natural number. So will this be true again? I mean, it will be same. The test, first of all, those two tests you cannot use there. And the thing is, when you saw this function f from n to sorry, real number, set of real number to set of real number, it was 1 1 and on to, right? When f is from R to R, how you can prove that? So you take x1 and x2. So for 1 1, suppose for 1 1, what do you do? For x1 and x2 in set of real number x, I mean from here mainly, if you take, then we will see that if f of x1 is equal to f of x2, then is that imply x1 is equal to x2, right? That will be the one-to-one definition. Okay. If the image is same, you are mapping from here to here. If so, you have x1, x2, two different two elements. So if they are going to same number, same f of x1 or f of x2, then it is not one-to-one, right? So you have to prove that if two things are different than x1 as 2, they are equal, then x1 also has to be x2. So then for this case, what is f of x is equal to 4x. So what you will get, x1, f of x1 equal to f of x2 will give you f of 4x1 equal to 4 of x2. That implies x1 will be equal to x2, right? I mean, it is one-to-one function, and on-to also one can prove easily, right? So if you have an element which is y, then you can find a number. What is the number? Will go to y. So if you put y over 4, which is a real number, that will be 4 times y over 4, that is y. So for each y you have a number y over 4 which maps to y. So f is one-to-one and on-to when f is a function from R to R. But this is not the case when f is a function from natural number to natural number, right? How is, you see the proof here. So if you have f of x1 is equal to f of x2, which implies 4x1 is equal to 4 of x2, that implies x1 will be x2. That is fine. So the function is one-to-one, but it's not on-to. When natural, instead of natural number we had real number, then it is on to also. But here it won't be on to, because you see what we said is what we have this. If you take 2 in this natural number set, can you have a number which maps to 2? So if that happens, then there will be a number x0 which will be 2. That implies 4x0 is equal to 2. And I hope all of you must know that this has no solution in the set of natural numbers, right? So this is this has no, this is not onto function. So we will not find any x naught such that f of x naught will be 2. So that implies the function is not onto. But if it is in a real number, set of real number, then it will be having the solution that is half. But half is not in the natural number here. So the beauty you see here, the function, this is one to one or onto, that depends on the domain and codomain. Okay. So that is the main thing I wanted to say here. You see the remark. So up to this, please, if you have any doubt, you please ask. Okay. So one to one and onto, these two properties depends very much on the domain and codomain of the function. So that was the first part of the little bit thing we did. So if you have any question, please ask me. I'll stop for some time. Sorry, who is telling? Okay, audio is not clear. Okay. You still have issue in the audio? Hello? Please talk maybe. Without, instead of messaging. Number one problem I will be discussing. Satya Prakash I will be discussing. But echo is still coming. Hello? Please unmute yourself and tell. Echo is still there. Okay. Hello? Hello? Now also? Hello? Now is less echo or? So that echo problem is still there. Okay. So then, yeah, if you have any question, please tell. You can unmute yourself and tell in, because I can't see the while presenting. Okay, the messages. You can unmute yourself. So Satya, he told about the first question. So first question, what we did, if you have a function f which is from natural number set to a set of natural number set. Sorry, this is the second question. Sorry. So first question mainly you can do it again here. Okay. So first question, what we did. So what I'm telling, f from set of real number to set of real number, that is 1 to 1 and on to. So what's the definition of 1 to 1? What I'm telling, so mainly you f of x, so fx is here given 4x. Okay, so I take f of x1 is equal to f of x2 for some x1 x2 belongs to the domain real number set. So this mainly x1 x2 you are taking from x1 x2 here. This f is a function which is going to some numbers. Okay. So mainly here that implies 4 of x1 will be 4 of x2 because the function is given like this. So what does that imply? That will give you x1 is equal to x2, right? That has to be the only choice. So and that is the definition of one to one. So this is one to one. Okay. And for one to, what you have to find for a given x naught, there should exist one y naught such that y naught will map to x naught. For any x naught, you should find a y naught here. So I took arbitrary x naught, let x naught be any arbitrary number which belongs to a real number here, mainly in this domain, codomain. Okay. So then what will see there exist. So what will be that x naught over 4? If I take x naught over 4 another number, that will be 4 times x naught over 4. That is nothing but x naught. So you have found a number x naught over 4 which are, so if you give me any number x naught, I can give you another number which will map to x naught. So that is the definition of onto means the function is onto, that's right. So this is like a game. If you give something, then I'll give you that. I can give you back also. For any choice of x naught, I can give you. So for any x naught in a real number set, I can give you another real number. X naught over 4 is a real number, right? So that will map to x naught. Okay. Any doubt, please? So now this is fine. First question, who was asking? Yeah, Satya Prakash, is it okay now? Okay. So now what we'll now move to, yeah. So these are the functions which are from, so all of you know, right? What is the e to the power x function? So e to the power x function, I mean exponential function mainly. So they are like this. So suppose you have this as 0 and this x-axis, okay, this is y-axis. So it will be like this, right? So it will intersect at 1. I mean, it will be 0, 1 mainly. 0, 1. And this will be going to 0. It is tending to 0 here, and it is tending to infinity here. Okay. And this is the e to the power x function. So if you draw the line parallel to, because e to the power x is a function from real number to real number, right? It's going to real number to real number. The domain is real number. Mainly the test will be the two tests I told. Those will be fine if the domain is real number. Okay. So now you draw lines parallel to, draw line parallel to y-axis. You see, whatever line you draw parallel to y-axis, that will intersect the curve, right? So what you can say that, so this function is 1 to 1, right? This function is 1 to 1, but it is not on to y, because if you draw a line parallel to x-axis, this line might cut here, this line might cut here, but this line won't cut the e to the power x function. So the graphical test is that e to the power x is 1 to 1 but not onto. So you can prove it also. So how you can prove it? So you take the fx1 equal to f of x2, That implies e to the power x1 is equal to e to the power x2, and take logarithm both sides to get x1 is equal to x2. So that will be 1 to 1. And but it won't be on to, because you will not get any number which maps to negative real numbers. So e to the power x from R to R is not onto function due to the fact that it won't give you a negative real number. So e to the power x mainly, e to the power x will be belongs to open interval 0 to infinity. I mean, I can say like this, I can write like this, e to the power x is nothing but this infinity to 0 for all x belongs to real number, set of all real. Okay. So yeah, so that's how you can prove using graphical test, also using the mathematical way. So the other two functions is this x square and x cube minus c. This also will be easy like this way. You have to mainly do these things. Okay. Is this fine? Okay. So it was the continuation of the graphical test mainly, graphical method. So we can see the graphical and non-graphical method using both. We can see the same result. So that is what I wanted to discuss.
Sir.
Yeah. Hello.
Hello, sir. For onto case, the line must intersect both negative and positive also.
Sorry. Yeah. Tell.
Sir, for onto situation,
Yes.
the line must pass horizontally in negative side also.
Which negative? No. It should, which line? First of all, it has to be the parallel to x-axis. If you are talking about onto.
Yes, yes, sir.
Yeah. So it has to be. It has to
Par-
cut the function, the
okay, okay,
graph. Yeah. It's not negative or positive. It has to
okay,
cut the function.
okay.
And
Sir,
this
but
PDF
in
that will be shared, then you will read that thing also. Okay. Yeah. Tell.
sir, in this graph, it is cutting at 0, 1 and this.
No, this is the y-axis is cutting like. See, the graph is cutting this, but you see this and right. So this is your, suppose this type of function is there.
Yes,
Whatever this function is cutting the y-axis at 0, 1,
yes,
but when you are drawing some other lines, that is also cutting some point. We don't need any which point, but at least one point should be there where this should cut. But you see, when you draw this line, it won't be cutting anywhere. It won't be cutting anywhere to the line, because the function will not come will not come beyond this line. Okay. So
okay,
whatever line below the x-axis, this is the x-axis, whatever line below the x-axis, that won't, those lines won't cut the function. But that has to happen if it is, if it is onto in whole real number set.
okay, sir.
Okay. So it's not onto on the real number to real number. So if the function was from e to the power x, if it is given that e to the power x from R to R plus, is it onto or not, then this will be onto, because the function domain already is restricted that R plus. So you should not then consider, this line. In that case, you should not consider this line, because this line is not in the R plus, not
Okay,
positive real, right?
okay, sir.
Yeah.
Thank
So
you, sir.
any other question, please ask.
Thank you, sir. I will.
Anyone else also? Okay, so if not, then we will move to the derivative of function, few functions. how to determine the derivative of a function. So yeah, everyone is okay with the whatever we did before.
Yes, sir.
Okay, okay. If you, any questions are there in the chat box, please let me know, one of you. Okay. Thanks. So, how you do the derivative of this type of function? How to do the derivative? Any idea? So first of all, like all of you know the derivative, how to do derivative, right? So if you have a function like this x to the power n, some n is there, or so let's say x cube. So derivative of this will be 3x square, right? 3 times x square. X to the power 5, this is x, 5 times x to the power 4, like this, right? Simple things are there, but how you do derivative of this function? This function is x to the power x times x to the power x, sorry, x to the power x. So what we do is, suppose fx is equal to x to the power x is given, so we transform it to ln of fx logarithm function, that will be ln of x to the power x. So all of we know now, as x is positive always, strictly greater than 0 is given, so x times ln x, that you can write. That implies limit, sorry. So now, if you take derivative ddx of ln fx, that will be equal to ddx of x times ln x. What does that imply? So from here, 1 over fx times f prime x, right? So derivative of ln x, that is 1 over x, right? So that's why 1 over fx come, and then it is like ddx of x ln x, which is ln x plus 1, right? So what does that imply? F prime x is equal to fx times ln x plus 1, that implies x to the power x ln x plus 1. All of you are okay with this? How we got this one? Yes, it was x to the power x. You don't know how to do it. You know x to the power alpha, and here x is a real number, any real number. It can be square root 2, it can be pi, it can be transcendental, any number. Okay, so you don't know because x to the power n, if it was x to the power n, you could do the derivative like x to the power n minus 1. So here you don't know that. So the fact you have to use here is you take logarithm both sides to deduce the form in a simpler form, and then do the derivative. Okay. So in
With x greater than or equal to 0, sir.
yeah, x is, you should take also x is strictly greater than 0. Okay, not also greater
They
than.
given mentioned that.
Yeah, tell. Yeah, I
No,
just,
they have mentioned like equal.
yeah, I made it. I only did the question, right? Made the question. So yeah, but it will be x should be greater than 0, because logarithm of 0 does not exist. See, ln of 0, you don't know what is the value, so it is going to mainly minus infinity, that type of, yes. It does not exist anyway, right? Ln of 0, logarithm function is like this. At 0 you don't know, it's going to infinity mainly, minus infinity, right? And here it is 0, at 1 it's 1 0. And whereas the e to the power function is like this, where it is 0 and 1, they have symmetry, like they are just if you have a line like y to the power y equal to x, they will be just image of one would be image of other through the y equal to x line. Okay, so you take, in this case, x is strictly greater than 0 for the, because log ln function, natural logarithm function. This is called natural log. I mean, it's log base e, that is nothing but ln. We denote this as ln. Okay. Yeah. Any question? I'll be waiting maybe for your question. Okay, so I assume that everyone understood the question x to the power x. You can try many other questions also like that. But we'll move to the next question, fourth question mainly. The diagonal element of a skew Hermitian matrix are either purely imaginary or zero. Okay. So here mainly you can, yeah, there's a, you know, the matrix, right? What is the matrix and then skew Hermitian matrix. Okay. So mainly for the skew Hermitian matrix, what we do, if you have a matrix, like suppose I am doing for a small matrix, okay, I mean less order matrix I will be doing here. So suppose you have some A, B, C, D. This is a matrix where A, B, C, D are, suppose let's say belongs to complex number. Okay. Okay. So if you have like that, so I am denoting A is this. What will be A bar? That is, it's like complex conjugate of this B bar, C bar, D bar. Okay. Right? And then if you have this transpose, that will be uh, okay, so A bar, C bar, B bar and D bar, right? This is like this. So whatever the case, so if you have a skew Hermitian matrix, the diagonal entries you see, that will be A bar is equal to A and D bar is equal to D. And for a complex number, suppose A is equal to alpha plus I beta, right? Then what will be A bar? A bar is alpha minus I beta. And when you make A bar equal to A, that implies alpha plus I beta is equal to alpha minus I beta. That implies beta is, sorry. So this is skew Hermitian matrix is given you, right? So that implies that has to be negative of this A star, A bar, the transpose, that has to be minus of it because of skew Hermitian matrix. So A bar has to be minus of A, that implies your alpha has to be 0, and for A, alpha is equal to 0 means A is equal to I beta, right? And B again, D also, it will be some I times gamma, similarly like that. So where beta and gamma can be 0 also can be, they are in real number, so they can be 0. When they are not 0, when they are 0, then A and D are 0, means the diagonal elements are here, so A and D, diagonal elements. So either A and D are 0, or we have they will be purely imaginary, right? So that's what the skew Hermitian matrix. That's how we can prove that the diagonal elements of a skew Hermitian matrix are either purely imaginary or zero. If you have any question, please ask. Is it okay? Shall we move on to something else? Then some other questions. Okay. Yeah. So here it comes some of the most important topic where you have it's called roles theory. So this is very interesting in where you can find the real life situations here. Okay. So first read this question, read this theorem. It says that the function we satisfy this condition, three conditions: continuous and continuous on the closed interval AB, differentiable on open interval AB, and the end points are equal. Then there will exist a number C such that f dash mean the derivative of f at C that will vanish. So mainly what it says here, you see, so if you have a function like this, suppose you have a function like this, okay? Sorry, I mean it has to be something like this. Mean that is here suppose A and here suppose it is B, and mainly these two are equal. This is FB and FA, they are equal. Then the theorem says that there has to be at least one point where if you draw the tangent line, that will make 0-degree angle with x-axis. Mean there exists, this is a C point, mainly f of C here, and the corresponding point is C here. Between A to B there will exist a function, between A to B there will exist one point where f dash C is equal to 0, means this implies f dash C is equal to 0 like this. So at least one, there is a number. There can be many number also, but the existence is given like this, where at least one number is there such that f dash C is equal to 0 if the endpoints are equal. Well, if you start going from a destination to another destination, say here A to B. So if you start with the car, I mean, if you go whatever way you want, if suppose it is a continuous, in the continuous road you are going, then at least once while going, at least once you have to be, your car has to be parallel to the line joining A to B. That's a big thing. I mean, otherwise you cannot go through a continuous and defensible road. So if you are going through the continuous and defensible road, when it's very smooth road, then at least once wherever like you want to reach to A to B point, so whatever way you go, at least once you have to be parallel to the line joining A to B. That's what this theorem says. Okay. So it's a very amazing and interesting example. It says that the car has to be parallel to the line joining A to B if the car is moving through a continuous and differentiable function, the line road. Okay. So that's one thing, but it has very wide range of applications in the mathematics. Okay, so that we'll do. So this is one theory, and this is another theory. So that's what we said. This if fa and fb are not equal, then there will exist one line c, one point c, such that f prime c is equal to fb minus fa over b minus a. Okay. Mainly, what is this fb minus fa over b minus a? This is the line joining. If you have a function like this, and this is fa and this is fb, the line joining these two has a angle, okay, and the angle will be this tan inverse of fb minus fa by b minus a. I mean, this fb minus fa by b minus a has that meaning. This point is a and b. Why it's not working? So this is a and this is b. Sorry. So the B point is FB and B. So B comma FB, and A point is A comma FA. Okay. So these 2 points, if we join, it will decline with the x-axis with tan inverse FB minus FA over B minus A, that angle, right? So this FB minus FB by B minus A, that point will be nothing but F dash C. That's mean value theorem says here. Okay. So these two theory mainly we will be using here for the for solving some of the questions. Okay. So the first question is this: if C0 plus C1 by 2 plus up to Cn by n plus 1 is equal to 0, where C0, C1 up to Cn are real number, then we can show that this equation C0 plus C1x plus C2x square plus up to Cnx to the power n has at least one real root between 0 to 1. Okay. So very interesting and very good result, right? I mean, very general result here. So you can say that any n degree polynomial, this is C0 plus C1x plus C2x square up to Cnx to the power n, this is nothing but a n degree polynomial, and it will have at least one real root between 0 to 1 if this condition holds. Okay. If this so if this condition hold, then we can say that the equation has one real root between 0 to 1. So the solution, what we do, we take the function fx is like c0 x plus c1 over 2 x square plus up to cn over n plus 1 x to the power n plus 1. So if we assume it like this, then what will happen? This fx, so fx is c0 plus c0 x plus c1 over 2 x square plus c0 n by n plus 1 x to the power n plus 1. So f of 0 will be 0, and f of 1 will be nothing but the given condition. We have given one condition is given, right? So f of 1 will be that given condition, and that implies that f of 1 is also 0. So f of 1 is equal to 0 and f of 0 is 0. So f of 0 equal to f of 1 and the function is polynomial type of function, right? So this will be always continuous and differentiable. So you can just easily write that. So once you have continuous and differentiable function and f of 0 is equal to f of 1, so you can use that f prime of c is equal to 0. So, but what will be the derivative of f? So derivative of this function will be, derivative of this function will be the c naught plus c1x plus up to cn x to the power n, right? So derivative of that is equal to 0 mean the c naught plus c1x plus c2x square up to cn x to the power n is equal to 0 at for some point, right? That's what it means. Okay. So now we'll so suppose we know that f(x) is a continuous and differentiable function on 6 to 15 interval. Okay. So let's also suppose that we f of 6 equal to minus 2, and also we know that f prime x is equal less than equal to 10. So what will be the largest possible value for f15? Okay. So what will be that? I mean, how to proceed? So you try to think from Rolle's theorem and mean value theorem mainly. Okay, think for some time. So use the derivative concept, and then you have a given number f of 6 equal to minus 2, and you have to find f of 15. You know some relation between that two, f15 and f6. That will be related to some derivative, and that derivative is also given to you. Yeah, so this is the hint for the solution. So yeah, we were in this question where we said, see, we can use mean value theorem here. How we can use that? So as I told this, this thing will happen. So f15 minus f6. Come back. Yeah, it's working. Yes. So this f15 minus f6 over 15 minus 6, this quantity you can always use, right? So you apply the mean value theorem here to get f15 minus f6 over 15 minus 6 is f prime eta, right? And that is always less than equal to 10, that is given from the equation, okay? So what you can get then, f15 minus f6, what is f6 value? Minus of 2 over 15 minus 6 will be less than equal to 10. That implies f15 will be less than equal to 90 minus 2, which is equal to 88. So yeah, so that is we can say that largest value can be 88. It cannot go beyond 88. So if you have, suppose, a function f of 6 is equal to minus 2 and f prime x is less than equal to 10, then the function's value at 15 cannot exceed 88, that value, okay? It's the largest value. See how the important the mean value theorem is giving you, okay? It can tell you the number, the f15 value of f15 cannot exceed 88. Just when, if you know f prime x is less than equal to 10 and f6 is minus 2, you can connect with f15, right? So if you have any questions, please ask now. Hello, I'll just check if you have any questions here. Okay. So please unmute yourself and ask if you have any doubt, okay? Yeah, so the questions we have done already. Now we'll move to indeterminate forms mainly, okay? So when you have this type of forms, which will be 0 by 0 form, infinity over infinity form, 0 times infinity also is not 0. People usually think 0 times infinity is 0. It's not always true, okay? Infinity minus infinity is not also 0. 0 to the power 0, it's not 1 just, okay? 1 to the power infinity or infinity to the 0. So these are all indeterminate form, okay? Although if you have this infinity plus infinity, that will, you can just think like this, but it will be infinity plus infinity will be infinity. That is not a problem. But infinity minus infinity, infinity minus infinity, infinity minus infinity is undeterminate. Okay? Why? You see, infinity minus infinity is just I mean, not, it's a very mathematical, but you can think like this. Limit x tends to infinity, x minus limit x tends to infinity x. This also you can write infinity minus infinity, right? But this is nothing but a 0 for this case. But when you have infinity minus infinity, you can also write as x tends to infinity. Why it is the first one? Why it is 0? Even I am writing, if I can write x tends to infinity x minus x, that is 0. Okay. If I again write it, this infinity you can write as limit x tends to infinity x plus 1 minus limit x tends to infinity x. That also will be infinity minus infinity form, and that is nothing but limit x tends to infinity x plus 1 minus x, that is 1, which is 1. Okay, it's undetermined mainly. So the infinity minus infinity, you can think also it is 0, you can think it's a 1, you can think any number, right? So what does that imply? That implies it's undetermined. It cannot be like one, you are subtracting from one number to another number, it is giving a different, very many numbers you are giving. So it's an undetermined form. So that is how we can say that infinity minus infinity is undetermined. It's not 0. But infinity plus infinity will be always infinity. 0 over 0 is undetermined always. Infinity over infinity is sorry, indeterminate form. And 0 to the power 0, all these things, these are all undeterminate form. Okay. So then in that case, we use L'Hopital. Okay. So what is that? So if you see, suppose if you have limit x tends to 0, if you have x tends to 0, fx over gx, suppose you have, that you can write as limit x tends to 0 f prime x over g prime x if fx equal to gx, sorry, not fx equal to gx equal to, if limit of fx equal as x tends to 0 is equal to limit of x tends to 0 gx is equal to 0 or infinity, both are equal and infinity. I mean, it's like infinity by infinity form. Sorry, if so, you can take derivative and you can go from fx by gx to f prime x over g prime x. So why I'm telling, so this is a couple of questions are given, but yeah, so for the first question easily you can see it here. Okay, so limit as x tends to 0 sin x over x. So you see limit as x tends to 0 sin x, that is also 0. Limit as x tends to 0 x, that is also 0. So it is 0 by 0 form. Okay. So what you do, you take derivative both sides. So ddx of sin x over ddx of x. What will be that? Cos x over 1. Limit as x tends to 0. All of you know limit as x tends to 0 cos x is cos of 0 is equal to 1. Right? So that is how you get limit as x tends to 0 sin x over x is 1. Otherwise, it would have been very difficult to prove some limit x tends to 0 sin x over x. It's both sin x is also going to 0, x is also going to 0. It's not like 0 by 0 is 1 because of that, not because of that. Okay. So, yeah, that's the one application of the L'Hopital rule, what I told. Yeah. So, any other question, any questions from this understanding this L'Hopital rule and indeterminate form? Yeah, if not, we will be solving all these questions only. Yeah, we'll see if some of the questions we can do. So how you can show that limit as x tends to 0 sin x over mod x? What will be this? We have now sin x over mod x. How to solve this sin x over mod x, sin x over mod x? Any idea? See, you cannot do, you know, right? Mod x is not differentiable I mean not differentiable at 0, right? So you cannot take just derivative here. You cannot do the cos x over modulus of x. So ddx of this mod x, this it, I mean it's, you cannot do like so, you cannot take derivative like this, okay? Because it's not differentiable function. So what you need to do here, you can take x tends to 0 plus and x tends to 0 minus, right? Limit x tends to 0 plus sin x over mod x. What will be this? When x tends to 0 plus, that implies x is positive. So what does that imply? Limit x tends to 0 sin x is to 0 plus sin x over x, right? This will be the same as like sin x over x, so that will be nothing but 1, because when x tends to 0 plus, sin x will be 0, sin x will go to 0, and x will also 0, so 1 0 by 0 form, and then again using that same thing. But when limit x tends to 0 minus sin x over x, sorry, sin x over modulus, that will be limit as x tends to 0 minus sin x over minus of x, right? What does that imply? This is nothing but negative of limit as x tends to 0 minus sin x over x. What is the thing? That implies this sin x over x is 1, and this implies it is minus 1. So you see, right hand limit and left hand limit are not same. So to exist, for the existence of the limit, the one of the first thing is, if you approach from any like side, if you have two sides, I mean if you want to find the limit at 0, so if you approach from this side or this side, both should be from both sides. If you approach to 0, then the value should be same. But here what you see, if I am approaching from right side, it is giving me the limit as 1. If I am approaching from the left side, it is giving me minus 1. So the limit does not exist. So limit does not exist. I will be writing D and E for does not exist for the rest of the lectures, okay? So this was the question 8b. We have done A and B. So similarly, you can do limit x tends to infinity, but it's not similar. Sorry. So how you do limit as x tends to infinity sin x over x? Any idea? Think about this. Can anyone tell me how to do this? X tends to infinity sin x over x.
So sin x can go at max to
Sorry.
sin x could range between -1 to 1, and x could go to infinity. So numerator could be maximum 1 and denominator is infinity. So it should be 0, the limit.
Sin x is belongs to 1 to -1. Good. Then
And denominator, which is x, can go to infinity. So
yes.
the limit should be 0 when the x tends to infinity.
Again tell sin x over what you are telling, tell sin x over x then.
And the denominator, which is x, could go as maximum as it could. So,
Yeah, are you telling like this?
yes, that is more accurate.
Yeah, so when x tends to infinity, you can assume that x is greater than 0. That is not a problem, right? X is positive thing, you can think, and then this will be fine. This will be fine. When this is fine, then what you can do? Take limit. Limit will be as x tends to infinity sin x over x. That will be less than equal to limit as x tends to infinity 1 over x, and limit as x tends to infinity 1 over x. That implies 0 is less than equal to limit x tends to infinity sin x over x less than equal to 0. So what will be the limit? So that mean a is less than equal to b and b is less than equal to a, both implies b equal to a, right? That implies limit as x tends to infinity sin x over x is 0. You see, when we took limit as x tends to 0, sin x over x was approaching to 1. When you were taking a limit x tends to infinity sin x over x tends to infinity, then it is 0. Okay? And don't make mistake by thinking limit as x tends to infinity sin x is going to infinity and do the calculation and make mistake. Don't make that mistake. Okay? Some people do this. Limit x tends to infinity sin x. Limit x tends to infinity sin x does not exist. Okay? Is oscillating between -1 to 1. It can never go to infinity first of all, and its limit also does not exist. So limit as x tends to infinity, limit as x tends to infinity, this quantity is nothing but limit as x tends to infinity sin x over x is nothing but 0 then. Okay? Whereas limit as x tends to 0 sin x over x, you had 1, and limit as x tends to 0 sin x over mod x does not exist. DNE. Okay. So up to this, any questions? Any question? Please ask. If you have any question, please ask. Otherwise, we'll move on. Okay.
Sir, what is the use of finding this?
Sorry.
What is the use of finding these limits,
Sorry.
all those things?
Yeah. So limit. How do you know about the function? How it behaves? So suppose don't think about this like a application of this function. Suppose if you have a function and you want to know its behavior after 1,000 years, after 2,000 years, after you don't know how many years means as much as possible after infinity. That's so yeah. The concept of infinity comes like that also, right? Like as much as large as possible after that time, what will be that function, or how that function will behave, how the time after some time this function might be a solution of a differential equation, right? At least you know differential equation. If you know the differential equation, the solution will be maybe this sin x over h. And when the solution is this, then you should know after 1,000 years or after 10 billion years how the function will be, what will be the value of that function. So always you don't know exact value, you cannot compute. So you take as much large as possible, then you know it will be going to nearby 0. After infinity it will be nearby 0. So we don't care about the very large things. Okay? So knowing the behavior of the function after very large time is also important in life, right? So that also you compute. Here it is x tends to infinity, you will see the time tends to infinity, t tends to infinity. That also you will find, you will face. Okay. So that's why the limiting behavior is always the function won't be what you think it will be. I will say like it won't be as it won't be very simple. It will be complicated function. So knowing the limit will give you the limit at that point. Might be you cannot find the limit at that point just by putting the value x equal to 0. See, as x tends to infinity, limit x tends to infinity here, limit as x tends to infinity sin x over x. This for this function you cannot just put sin infinity over infinity, right? Or some other singular value. You cannot do that. So by knowing the limit, you mainly knowing the function's behavior after large number of value without putting without putting the sign infinity over infinity, that type of thing. I mean, that you have to determine like this, right? So do you understand what I'm meaning? Who asked this question?
Yeah, yes, sir, I understood.
Yeah.
But
Who
what is the use of finding this? Why I need to find sin x by x limit extends to 0?
See, sir, if you know sin x over x, you will know maybe some other function like this. Is to give you one example here, how to find the limit. So maybe exactly this limit won't be like applicable for you, but you can have some other difficult function like sin x over x. It's a kind of maybe same type of it will be, but those will be a solution of a differential equation. And you know, when you have a solution of a differential equation, you should know after 1,000 years, after 10,000 years, after some billion years, what will be the like if let's say some population dynamics you have. There also you have something like differential equation. You have the differential equation will have a solution, and you should know the how the population will be after 10,000 years. You might one might want to know that, right? So in that case, you just putting limit as a very large infinity number. You can guess from the beginning that it will be, it can't go beyond this, right? So the knowing exactly the sin x over x might not be applicable for your case, but that type of concept will be applicable in many other situations. That's what I mean. Hello. Whoever is asking, may I know, are you from an engineering background, right? So you are maybe or mathematics background.
Yes, sir, I am from.
Sorry, I can't hear you.
So I'm final year aeronautical engineer.
Finally, you are not getting.
Sir, I am final year aeronautical engineer.
Final year engineering. Okay, okay. Yeah, I don't see. So it's not all the places it will be applicable, but knowing the behavior and the limit, all these things, it will be applicable in many analysis where you don't know about the functions by by seeing the function you might not know, but the limit, if you know the limit, that will be the thing. When you know the limit, then you know the behavior at that point. Okay, so that's why these type of things are useful. Okay. Yeah. So any other questions? Maybe next day also we can discuss about these things. But I will say this is for first of all some analysis, and of course it will have some application. This is like the finding out the limit, like from this sin x over x, you can do some other for some other functions. The behavior, knowing the behavior of that function will be very important in our real life applications maybe. So that's why we do some limit argument. Okay. So if you have any other question, please ask. Otherwise, we'll move to the next part, which is Taylor's theorem. Any questions? Please ask whatever question you have in your mind. If not today, I can't give the answer. Then I will give you maybe in the next class. Okay. But please ask. So Taylor series is like this, where it says that if you have a function which is continuously derivable, means it says n plus 1 continuous derivative, then you can write like this polynomial plus some remainder type of terms. Okay. So mainly the remainder term, as much as you take the n value, this bigger n value, you get Rn will be going to kind of 0, right? And then what will happen is fx, so it says that if you have a function like this, you can approximate by some line or some polynomial. Is for line it is x f will be fa plus x minus a times a prime a, but I mean you can approximate by using polynomial. Okay. So we'll see in the we see in the when people do the numerical analysis and all this, the approximating function using the polynomial is very important, because exactly that function maybe you cannot, that's very impossible maybe in the real life we get the exactly that same function, but if we can get a function which is very close to that function, that is also fine, the error is very less, and that approximation we can do by using polynomial or the piecewise constant polynomial or piecewise constant, so piecewise polynomial function or piecewise constant function. Using that, we can approximate that function, and that is given by this theorem that any function which is continuously derivable, that can be approximated by a polynomial. Okay, by a polynomial or by many polynomial or the piecewise polynomials. Okay. Okay, so using that or the using the Taylor series or the mean value theory, we can show that this 1 minus x square over 2 factorial is less than cos x when cos x is not equal to 0. Okay. So how you prove this thing? This 1 minus x square over 2 is less than cos x always. So see, here it is a very simple function cos x, you know everything is fine, but you might want to know about some functions, like the function's behavior, but explicitly the function by putting value you don't know. But if you know some other function which is much simpler, then you can get to know about behavior using the other function also, right? So here you see this 1 minus x square by 2 less than cos x, even though you can prove what will be the application, people may ask. Okay, so see, instead of knowing nothing, little bit thing knowing it's better, right? Okay, so here it is cos x, that's why you know all the things, but sometimes the function will be different, but the similar analysis will be followed there also. So you don't know exactly what is the value of cos 1, but you know that cos 1 will be greater than or equal to 1 minus 1 square over 2 factorial. That is half. I mean, instead of knowing nothing, at least you know cos 1 will be greater than half. That is the application of knowing the 1 minus x square over 2 factorial is less than cos x. Right? One of the simplest thing. So now, but how to prove it? This cos x, so I take fx is equal to cos x minus 1 plus x square over 2 factorial. Okay. So when you take derivative f prime x, that will be minus sin x plus x. Okay. And what we get is, okay, so f at 0, you see f at 0, sorry, I'll just, yeah, f dash x is this. And we know you see, if we draw a sin x line, it will be like this, it will go on, and it will be like this, okay? So sin x is always, yeah, it will be like this. So when x is greater than 0, sin x will be less than or equal to x. I mean, then x minus sin x is greater than or equal to 0. So in the f prime x is greater than or equal to 0 for all x greater than or equal to 0, right? That implies fx has to be greater than f0. That implies cos x minus 1 plus x square by 2 factorial has to be greater than 0, because f of 0 is cos 0 is 1, 1 minus 1 is 0, plus 0 is 0. So that implies cos x is greater than equal to 1 minus x square by 2 factorial. Okay, so that's what you needed to prove it here. So using mean value, that is using mean value theorem. You can same thing you can do for Taylor's theorem also, using Taylor's theorem. How you do that? The same thing, Taylor's theorem. You have fx equal to here fx equal to cos x, you choose for the Taylor's theorem. It's alternative mainly you are doing. Alternative. Okay. Fx equal to cos x. Then what will happen? According to the Taylor's theorem, fx you can write as f0, because the cos x function is derivable and continuous. Those things are, all those nice properties are there. X minus 0 times f prime 0 plus, yeah, so what will be this? F prime 0 plus x square by 2 factorial f0 x f dash 0 minus x, yeah, x square by 2 factorial f double dash 0, right, plus x cube by 3 factorial f prime some xi, where xi belongs to 0 to x, right? That is the Taylor's theorem here. I have already given the definition of the theorem, right? So if that is so, then what you can do here, that implies cos x will be always equal to cos 0 is 1 plus x time f dash x is fx equal to cos x, means f dash x equal to sin x minus sin x, and at 0 the value will be 0 plus x square by 2 factorial f double dash 0. What will be f double dash? F double dash will be minus cos x. So f double dash 0 will be minus of cos 0, which is minus 1, plus some other term which is x cube by 3 factorial times sine of xi. Okay, that implies cos x minus 1 plus x square by 2 factorial is equal to x cube by 3 factorial sine of xi, which is greater than 0 if x greater than, which is greater than 0 if x greater than 0. Even though x less than 0, then also it will be 0. So if always, I mean, it will be always greater than 0. Why? It has x cube and sine xi. So when x is greater than 0, then xi will be also greater than 0. So sine xi will be 0 in each interval you take, that will be greater than equal to 0, right? Wait a minute. At least you can show that in a 0 to pi by 2, suppose 0 to, let's say 0 to pi by 2, you take 0 to pi by 2, in that interval it will be greater than equal to 0. Okay, and if even if you're taking minus pi by 2 to minus pi by 2 to 0, then also it will be greater than equal to 0. For other case also you can do in the similar other way, but at least for this two interval, in the interval of 0, you can show that this is greater than 0. That implies cos x will be greater than 1 minus x square by 2 factorial. Okay, so that is using mean value theorem and Taylor series. Using both, one can show that cos x will be greater than 1 minus x square over 2 factorial. Okay. Yeah, so we'll be moving to the next question. Yeah, so we read the question. The thing is, it is given that f is a 3 times divisible function such that f of minus 1 equal to 0, f of 1 equal to 1, and f dash 0 is equal to 0. Then use Taylor's theorem to show that f triple dash third derivative of f at c some points belongs to minus 1 to 1 is greater than equal to 3. Given these properties, you have to find out a way. You have to prove that this is greater than equal to 3. How you do that? You have 3 conditions given. F of minus 1 is equal to 0, f of 1 is equal to 1, f dash 0 is equal to 0. Yeah, so this is the hint for the proof mainly. So what you do is this. Yeah, so you know that fx is equal to f0. So using Taylor's theorem, so he is using fx will be f0 plus x times f dash 0 using Taylor's theorem plus x square by 2 factorial f double dash 0 plus x cube by 3 factorial f triple dash some xi, right? Xi belongs to 0 to x. Okay, I mean it is, I can write this is like xi x. Okay, more importantly like this. So between any two x and 0, I am using the Taylor's theorem mainly. Yeah, use Taylor's theorem on 0 to x if x greater than 0, or on minus x to 0 if x is less than 0. Okay, x is less than 0. Yeah, x to 0 if x is less than 0. Okay, so that you can use to get the above equation identity. Now it is true for all x. So if I put f x equal to 1 to get f of 1 is equal to, why I am putting this, you know the value of f of 1. So f of 1 will be equal to then f dash 0. What is the f dash 0 value? F dash 0 is also given 0. So erase this thing. See, I am writing from here mainly. So f dash 0 is 0. So x square by 2 factorial f double dash 0, that we don't know, plus x cube by 3 factorial. Sorry, x cube, not x cube, it's 1. The value you are putting for x is 1, so it will be 1 f triple dash xi 1. Okay, right? This is correct, right? So then now we'll put f equal to minus 1, x equal to minus 1. That will be f of minus 1 will be f0. Sorry, yeah, f0 is also there. So please make a note, f0 plus. So f0 plus 1 over 2 factorial, because it's x square minus 1 whole square, that will be also so that will be 0 plus, not plus, it will be minus 1 to the power minus, so minus 1 over 3 factorial f triple dash xi minus 1. Okay, yeah, so Exactly. So this is correct. So now this is a equation 1 and this is equation 2. So make 1 minus 2. That will give you f of 1 minus f of minus 1. That is equal to, see, these two are same now. So you have only 1 over, so 1 over 3 factorial 1 over 6 f triple dash xi 1 plus f triple dash xi 2. That implies f of 1 minus f of minus 1. So what is f of 1 is 1, f of minus 1 is 0. So 1 minus 0 is equal to 1 over 6 times f triple dash xi 1 plus f triple dash xi 2. That implies f triple dash xi 1 plus f triple dash xi 2 will be 6. So you got that there exists xi 1 and xi 2. Sorry, it says xi 2 is mainly correspond to this 2 xi 2. So xi 1 and xi 2, these two variable, this the addition of these two number is equal to 6. So either f plus xi 1 is less than equal to 3. What do you need to prove that? Sorry. Yeah. Either is greater than equal to, sorry. So the addition of two number is 6. So can both of them is less than, strictly less than 3? So addition of two numbers is equal to 6. So can the both number be less, strictly less than 3? It cannot be, right? So that's why either this will happen or this will happen, has to happen. Okay, this or this, from here, maybe from this one can get this or this. So in any case, what you will show that this f prime c, f triple dash c is greater than equal to 3 for some c belongs to minus 1 to 1, because this xi belongs to minus 1 to 1, any number. Okay, see, xi 1 here you have that your xi 1 belongs to 0 to 1 and xi 2 belongs to minus 1 to 0. So whatever the xi 1 or xi 2, it will be belongs to minus 1 to, which is subset of minus 1 to 1, which is subset of minus 1 to 1. So it will, whatever the number, it will belongs to minus 1 to 1, and you have proved that one of them, at least one of them will exist such that f triple dash xi is greater than equal to 3. Okay. So that was the proof, I guess. And okay, I will wait for some time to ask us to get the questions. So I am kind of end of the this class, today's class. But if you have any questions, please ask. Guys, please ask questions. Okay, if you have any questions, please ask. Also, you can reach me by my mail. Also, mail ID. I think everything is shared already with you guys. Whatever the my mail ID or my contact number, not contact number. I think mail ID it will be shared. You can reach me out that there. If you have any further questions, also you can. I can give you the contact number also. Okay. But yeah, not of course here because this video will be shared in the YouTube as per the guideline given. So yeah, I cannot give it here, but I will be. You can if you send me a mail or something, I will be. I will be giving there maybe. Okay. So yeah, you learn something at least that will be good for me because this is not something which where like you have to pass. You have to pass. This is not there maybe. But if you learn something that will be benefit, that will be very good for you. Later it will be very useful for you. Okay. So these are some trick you if you know then you can use in many applications in the engineering field. Okay. So try to be attentive at least come every day like not every day whenever I have the class Saturday is 6 to 8 p.m. So I'll be trying to give more. I'll try to make the session more interesting, more beneficial for you. So I'll try my best. So today this was the first class, and yeah, I had no experience of doing this online with this much people. I used to teach, but not in this big platform. So yeah, I'll be, but the next class I'll be doing better. I hope. So please come join. We'll learn together. Okay. So I'll be still waiting for at least 5 6 minutes. If you have any doubt, please ask. Otherwise, you can leave also. Okay. So okay. Before that, so these are the some references which is also given in uh, Jitendra says Professor Jitendra Kumar. He also given this all these book references. Yeah, and thank you for your attention. Okay. So this is the book name. You can follow. Yeah, thank you for your attention. Bless. Anyway, you have lost 10 minutes for any questions or doubt. Any you can ask me. Okay, here I'm still here for 10 minutes. Thank you. Yes. Anyone?
Sir, can you share your mail ID, sir?
The mail ID is already shared, I think. So anyway, I can give it here also. You may reach by this is Rahuldev. I mean you. Okay, let me write it clearly maybe.
கீழே
Sorry.
போடுவோம்.
So I am from ISER TVM. Okay. So this is my mail ID. So Rahuldev 19. My name is Rahuldev Ghorai. So the first name, then 19. So there's some batch number and then at the rate isertvm.ac.in. So you can reach me through this in this mail also. Yeah, there's a one only to like this one mail is enough I think because I'll be like active in this mail ID. Okay. Any questions, please ask me. Okay, no hesitation. I'll be trying to answer. I'll be trying to give you give you reply back as soon as possible. Okay. as much as early I can. So this is my mail ID, and you can put the questions also in some sessions are there. I think some forum, question answer forum or something is there. There also you can put your questions. We will be giving you answers, or you can reach me through this mail also. No issue. Okay. So any other questions? Otherwise, I'll stop this session. Waiting for your questions. Okay, so I'll end this session quickly. Okay, thank you everyone.
Satya Prakash, I have shared already the mail ID.